This one is about a practical to measure the internal resistance and the EMF of a cell. Most of this should just be memory work. You need to have a really good memorized description of all of those practicals, all those 16 practicals for the syllabus. Alright, so hopefully you're going to look at this and think, yes, thank you very much, this is a simple describe of a practical which I have memorized, one of the 16 core practicals I've got to remember. This is to determine internal resistance. I know all that, that's fine, I remember it. It's where I've got my little graph where I plot terminal potential difference on the y-axis and current on the x-axis, and I get a gradient with this being the gradient and this being the y-intercept. Firstly, I've just got to tell them the procedure. Let's include a circuit diagram. Well, I'm going to use a ruler. I didn't at first here because, well, in year 7, I was taught to use a ruler for my circuit diagrams. There's my cell, and I've told it's a cell, so I haven't drawn a battery or a power pack. And I'm going to need a way of varying the resistance, the load resistance. There's my resistor, which I need to be able to vary, and I want to be able to measure the current, so I'm jolly well going to need to put my ammeter in series. And then lastly, I'm going to measure the voltage, the terminal PD, so I'm going to need to put my voltmeter across my resistor there. So that's nice and simple. Got my marks, got my first mark there. Okay, so essentially what we're going to do is we're going to record terminal potential difference and current for a range of load resistances. Okay, those range of load resistances is by changing the variable resistor. So I might say use the full range of the variable resistor for 10 data points. Okay, well the marks are for the diagram, they're for the pairs of these, so terminal PD and current, and for having a range with around 10 data points. Okay, between 5 or 10 is what it says in the mark scheme. I always like to say 10 because I think you can't really see a trend for less than about 7 points. And if I've got 10 data points, then I give myself room for 3 anomalies. That's just sort of a good rule of thumb. Really, if I was doing that, I'd probably do a few more than 10, but 10's a good number. So next, describe how you'd use your results to find a value for the EMF and internal resistance of the cell. Hasn't told me to do this, but I think I might as well just sketch the graph as I know it. I and V there. You're going to get a straight line graph, hopefully, with minus R being the gradient and the EMF being this point here. Okay, I do in fact have a video where I go through this, which I'll try and remember to put a card to here. How we're going to use this? Well, I think I've stated where I'm going to plot my V and I, but I might just put that in words as well. And then I've said that the y-intercept is the EMF, and lastly the gradient is minus R, the internal resistance. Why is that? This is not part of the mark scheme, but let's just go over it really quickly. Well, the EMF is defined as the terminal PD plus the lost volts, which is the current multiplied by the internal resistance. Okay, so this is the PD across the variable resistor. This is the PD dissipated by the internal resistance. So this now looks very much like a graph y equals mx plus c. It's just kind of squidged around the wrong way. So if I move this across here, then I get EMF minus IR. This is now y equals c plus mx, or where it really xm, but it's the same idea. Minus r is the coefficient of our x variable. Okay, hope that makes sense. This is a learn one by heart kind of question. What they've done on the other side is they've given you another graph, which is not the graph that we've just discussed here. So that's where they're asking you to be quite resilient. Can you work with different trends, different graphs, similar ideas, but not the same variables? So here they tell you what this graph is all about, first of all. This is for a rechargeable battery which has been recharged a number of times, and it shows that the internal resistance increases as we keep recharging the battery. So the manufacturer's claim is that after 500 charging cycles, the PD, the terminal PD, will be more than 99% of the terminal PD when new. So I hope the first thing you're going to think is, well, I need to get data off from 0 when it's new and from 500. So let's just do that. I can see 0. R0 for 0 is 310 milliamps, and R500 is, I'm going to use the line, not the data. It's quite an important thing. What's that? 327 it's closest to from the graph. Okay. What do I need to work out? I need to work out the terminal PD here and here. Hopefully, you remember from the last part of this video where I actually used this definition of what EMF is, and we're told the EMF at the top here, 3.6. So I can actually use this rearranged form that I've already done. V is EMF minus I little r. Okay, so I essentially need to just do that for here and for here. And it tells me the current, the supply current is 800 milliamps. I've realized an error that I've made here. I'm talking about resistances. Clearly, they should be numbers of ohms. Okay, and I'm also going to straight away just convert them into ohms, because why not? And here my current, I equals 0.800 amps. Okay, so now I can do this. Oh, my EMF from the top was 3.6 volts. Okay, so for naught, let's call this V naught. EMF 3.6 minus 0.8 times 0.31, and V of 500 is 3.6 minus 0.8 times 0.327. Okay, calculate time. Okay, the terminal PD when new is 3.352 volts. Okay, what about when it is 500 charges in? 3.3384. I might as well just use the sig figs for now. I've got some marks now because I've actually read the two things from the graph correctly, and I've got my two potential differences. Now I'm going to go ahead and work out if the manufacturer's claim is correct, which is that this is still more than 99% of this. So how do I do that? Well, I just do the ratio of this to this. So V500 over V naught, which is 3.3384 over 3.352, which is 0.9959, or in other words, that is 99.6%. So the manufacturer's claim is correct. It's 99.6 is greater than 99%, so manufacturer is correct. Okay, I hope that all makes sense. Do not forget these points here. Explain whether it supports the claim. Okay, they are looking for a final statement. This little bit here. Can you work out the ratio, make a final statement about that based on the data? Okay, so whilst the first 5 marks of that were just describe marks, just really regurgitating what you've remembered, the last ones used a bit of analysis on a graph, and they've purposefully given you a graph which is similar looking in shape, in a straight line, to the one you've just been asked about in the previous question. Really, it's just getting data by interpolation and then using data to justify a statement. There will be loads of questions like that where they're asking you to justify or criticize or evaluate. You need to figure out what calculations you can do to actually evaluate or justify or refute any claims.